Okay, let me start today's session with introduction to the inductance of a three-phase line with more than one circuit. So as soon as when you hear the term with more than one circuit, you can generally recall what we did in case of the other one, that is the previous derivations. It was for the single phase derivation. So now if I have more than one circuit, it is a double circuit line which is being present there. So once I consider this three-phase transmission lines which are being working with more than one circuit in parallel, so there is a negligible mutual inductance between the circuits if they are widely separated. In this case, the inductive reactance of the single circuit is half of the individual circuits which is to be considered. So, but in this case, the actual method of GMD is to find out the inductance of each phase. Yes, as you can see, the inductive reactance of a single circuit is half of the individual circuit which is being considered alone. So, but in this case, in the method of GMD, so you need to find the inductance of each phase, which is being done by considering the different conductors which are in parallel as the strands of one of the composite conductors which is being present there. So, if there are more than one circuit in parallel, then it is desired that the equivalent circuit should have low inductance value. So, this is the main aim of it. So this is the main aim where you will be having the lower inductance value which is being present there, and this can be achieved with lower value of dm and higher value of ds which is being present there. So in order to achieve this individual conductors, like how do we achieve it, and it is being separated by widely as possible. So and the distance between the phases is being kept small. So thus in case of a double circuit line, so conductors are arranged in the second figure which has been shown. So I'll show you later on how do we show the second figure. So next one, what I can generally see is you'll be having the lower value of the inductance. The main aim is to find out the lower value of the inductance with the arrangement which is being done in the first figure. So the use of the double circuit line increases the reliability of the power supply in case if one of the circuit becomes inoperative due to some reason. So why we need to go for the double circuit lines? So double circuit lines. So the main aim is to have first one which is the low inductance value, and due to some due to when one of the lines is inoperative. Okay, so these are the conductors which are connected in parallel and kept on the either side of the tower there. So next one, what you can understand from this, let me draw the system which is being present there, and what you can generally see is x, y, z, and later on you will be having the positioning of the conductors done in such a way that it is x dash, y dash, and z dash. So this value has the inductance to be lesser, and the other one you will be having the inductance to be more. So as you can see, x and x dash, L and y and y dash, and z and z dash which is being present there. So this forms, or this creates a value of the so this creates in such a way that it leads to lesser value. I mean the inductance here, it is having the lesser value. Inductance having lesser value and inductance is having more value which is being present there. So next what I can generally do is, so let me go to both the symmetrical spacing first. So let me derive the inductance of a three-phase double circuit with symmetrical spacing. So which is the circuit that I need to take? Either I need to take this figure, which is, let me write it as figure 1. Let me write this one as figure 2. So whether I need to go for figure 1 or figure 2. Why? So I'll be selecting figure 1 for the option because in such a way that the value of the inductance is to be less. So considering a three-phase double circuit line with the conductors being placed at the vertices of the regular hexagon which is being shown in the figure there. So if I consider the regular hexagon as you see here, so you will be having the distance from x to x dash to be d plus d, which is 2d. So d plus D, which is 2D. And next one, what I can suggest is, so remaining distances such as Z to Z dash. So this one is generally taken to be D. So the same parallel distance which are being present. So if I want to calculate this, I'll be going for the Pythagorean theorem. So you can know the hypotenuse, you know the base distance, and you can generally find out this distance which is being given there. So this is the center point. Let me mark this as the center point, and this distance is d by 2. How it is given as d by 2? Let me tell you now. So this one is the center point of the conductor. So this one is the same distance, and here you will be taking it as d. Why? So here you know the distance between y dash and z dash. You generally take it to be the hypotenuse. So you can use the root of a squared plus b squared being present there. And this one is a, and this one is the other side which is being present there. So next one, again the same equilateral triangle. We can form it here, and here also we can form the same equilateral triangle, and here also we can form the same equilateral triangle there. So this point is marked as a center, and here you are left out with y and y dash. So again you will be having z and z dash. Again it is 2D. So you can see that between x and x dash equals y and y dash equals z and z dash, all the conductors are said to be having twice the distance that is being present there. So 2 times the distance that is being present. So that's the value of it, what you can find out. So next, what you can generally understand is, so how do I find out the remaining distances which are being present there? So first one, you can go for the Pythagorean theorem easily. So dxy is to be found out, that is this distance. So dyz, which is same as dyz, this distance is same. Okay. So what do you need to do? You need to take the Pythagorean equation, which is being present there as root of a squared plus b squared equals distance xy. So that is being found out. So next you can find out in the same manner dyz, y dash z dash, and dx dash y dash. So this is being present here as d. Generally it is being given as a d, dxy dash. So it is root 3 into d. So this point is taken as the midpoint. Let me write it as the midpoint here. So again, all the all the distances are being present there. Okay. So you can move to the flux linkage equation directly. So that's the main aim. Before finding the inductance, you need to find out the flux linkage of the conductor that is being present there. So to find out the flux linkage, again I'll be considering 3 conductors which are being present there, which forms one circuit, and x dash, y dash, z dash are forming the another circuit which is being present there. So let us find out the flux linkage of the conductor due to the current in other phases. So let me tell you how to write this equation 1. So what you can generally do, x and x dash, y dash, z dash being present there. So this is x dash, this is y dash, this is z dash being present there. So what you can generally do, you need to have 6 equations that is being present there in the equation 1. So it is having 3 sets of equation. So you are having 6 equations, or you can have 6 terms which are being present there in equation 1. Okay. So now let me talk about the first one, which is 1 divided by r dash. So how did I get this 1 divided by r dash? It is nothing but the GMR. So geometric mean radius that is being present there. So this one, it is d x to x dash. This distance is being present. Next, you will be having dxy, that is due to current I, xy, that is dxy. Next, dxy dash, dxy dash. Next, xz dash, dxz, dxz dash. So that is being present there. Okay. So now how to write the equation, you already know it. How to come to the final flux linkage equation, let me show you now. So as you can see, this term and this term, all the distances are being represented with equal distances, what we have arrived at the previous equations. And you can find out ix plus iy, ix is being a separate term there, sorry. Iy plus Iz is being taken separately as a common factor, with the other common factor being represented there. So next, what you can generally use is Ix plus Iy plus Iz equals 0, and what I can generally write for Ix is minus Iy plus Iz. Okay, so if I take the other way, minus Ix equals Iy plus Iz being present there. So if I can substitute it, I'll be having this equation alone. So Ix and Ix are being present there. So 2 into 10 power minus 7 into Ix ln of root 3 d squared divided by 2d into r dash. So the d term and the d term get cancelled here. So 5x is being present. So 2 into 10 power minus 7 Ix ln of root 3 d divided by 2 r dash is being present there. Okay. So these are the terms which are being used there. And how do I find out the inductance? That is due to the conductor X. Lx equals 5x divided by Ix. So that is equal to 2 into 10 power minus 7 ln of root 3d divided by 2r dash, that is Henry per meter there. So if I want to find out the inductance in each phase, inductance in each phase is being carried out by the half of the term which is being present there, half into Lx. So half into Lx, what I can generally use is half into 2 into 10 power minus 7 and this equation which is being present. So you are left out with the final equation called for the inductance of each phase. So why did I generally take half of it? Is the conductors are connected in parallel. So once you have the conductors are connected in parallel, so to find out the overall inductance, you'll be going for half of it. So assuming that the conductors are of equal value, the inductance of each phase can be carried out by half into inductance per conductor. So this is how you can generally come to this equation. If you can analyze, let me go through it quickly once again. So you can see that all the equations are being written with respect to 5x, and you can make an effort to write it in terms of 5y. You will be getting the same result at the end. Moving on to the numerical problem. A double circuit 3-phase 50 Hz line, 3-phase line has a conductor at the vertices of a regular hexagon. So you need to find out first what you need to find out. Is it a double circuit line? Yes. Is it a 3-phase line? Yes. And it is a regular hexagon. So it is generally double circuit, 3-phase. I mean, generally it would be a regular hexagon having each phase having the forward current path and the return current path which is being present. So each side of the regular hexagon is 3.5 meter. That is a polygon. That is the diameter of the conductor is 2 centimeter. Find the inductance and inductive reactance of a line per phase per kilometer. So that is the value that is being present there. So if I want to find out per phase per kilometer, so from Henry per meter, I need to convert to Henry per kilometer, which is being present there. Okay. So next, what do I need to do? I need to find out the angles and I need to find out the distances which is being present there. So these are the angles that are being present. Yeah. So let me find out the angle as sine 30 degree. How did I find out it as sine 30 degree? So if you can generally see, it is 360 degree divided by 6, which is being present there as 60. That is, this is 60 degree and this is the angle that was being present there. And you can find this angle to be 30 degree. And what you can generally use here is sine 30 with respect to this angle that is being present there. So that is how you can find out 3.5 into sine 30, that is 1.75 meter as the distance bm. So this is, let me write it as bm. Yeah, let me interchange this as bm. Generally, I'm giving you a distance there. So that is being given as bm. Okay. So next, in the same way, sine 60 degree, I can generally write it as am divided by ab. That is sine 60 degree. So you are having am distance to be 3.031 meter. So diameter of the conductor, that is each of the conductor is 2 centimeter, and GMR of each conductor, that is 0.7788, that is the diameter of each conductor divided by 2. So that is being present there. Okay. So later on you can find out 0.7788 into 2 into 10 power. This is the diameter, and diameter divided by 2 is generally a radius. So you can find out whatever the things that are being present there. Yes, this is a regular hexagon. As I told you, you are having the angle which is being present there. This one is generally 360 degree divided by 6. 6 ones are. So each angle, each side, once you get it across each point, this one, okay, so this one is generally 60 degree, 60 degree. So what I told you, it was generally with respect to one more base point which is being taken. So this angle is 30 degree there. So this forms the base. Okay, the right angle triangle is like this. I can rewrite it. So this one is 90 degree, and this one is 30, and this one is 60 degree, which is being present there. Okay. So next, if I want to move on, I need to find out the remaining distances. What I can generally use is the Pythagorean theorem to find out dBA dash and dCC dash, which is equal to dAA dash and dAB dash, which is being present there. So use the Pythagorean theorem using Pythagorean theorem. Okay, I can find out dBA dash, dCC dash, and D is generally given in the problem as 3.5 meter. So what you need to do is you need to find out D and R dash there. Okay, so it has already been given. You can generally make a simple substitution and you can find out what is being given there. So this is in terms of Henry per kilometer. So inductance per phase per kilometer is 1.9928 millihenry. That's what you can find out. So inductive reactance XL equals 2 pi FL. So this is L there. So this is the value of L. So XL is given as 0.3747 ohm, which is being present there. So XL equals 0.3747 ohm, which is being present there. Okay. So this is one of the simplest derivations and a simple problem. If you know the geometry, basics of geometry very well, you can generally analyze any problem which is given of that format. So next one, what do I need to do is, I need to analyze the inductance of a three-phase double circuit with unsymmetrical spacing but transposed. So considering a three-phase double circuit line having conductors which are unsymmetrically spaced, and what you can do is, so the line is said to be transposed. What do you mean by transposed? The conductor occupies the position of each of the conductor after certain interval length or distance of a transmission line. So if I want to find out how it is, I can generally make an arrangement for position 1, position 2 and position 3 which is being present there. So X, Y, Z, yeah, X, Y, Z, next X dash, Y dash and Z dash. So for the next position with given distances, so this distance is H, this distance is also H, this one is also H, and the distances is D alone. Yeah. So if you want to find out this distance, it is M and N there. Okay. So all the distances are being given. Now I need to transpose for a given transmission line length. So let me make the transmission line length as 300 kilometer or 600, whatever may be the length of it, or generally let me go for 100 kilometer length. So I need to divide it by 3 because they are having 3 transmission line conductors which are being present there. Okay. So what I can generally come across is replacing the position of the conductors accordingly. So X is being replaced with the Y here. So as you can see, so as soon as Y takes the position with respect to Z. So Y moves to Z here. As you can see, X and Z is being moving back here. So in the same way, again, X dash moves here. So Z dash moves here and Y dash moves here. So that's how I can generally come across the remaining position also. This is the second interval. This is the third interval which is being given there. So the distances would remain the same. All the things, as you can see, the distances in all the cases, the distances in all the cases are M, N, M, N, H and D which is being present there. So all the distances are one and the same which is being present there. Okay. So what we can generally understand from this is, so you need to find out the flux linkage of conductor X in position 1. So flux linkage of conductor x in position 1, again you are having 3 different set of terms which are being present there, and totally 6 terms in equation 1. 6 terms in equation 1. So what do I need to do? 1 by r dash, 1 by n. So the same thing what I have done, x dash, y dash, z dash. So this is x dash. So this one is with respect to GMR, x and x dash, whatever that's there. So that is 1 by n. So that's how you take the general distance there. Next one, you can generally have the distance to be 1 by d. So simple formula, if you can recall simple formula there, so you'll be able to understand it better. If you can recall the transposition of lines derivation, what we have done for single circuit line. So we are extending the same concept to the double circuit line also. Next one, what do I need to do? I need to do for the position number 2, position 3. So this is equation 2. This one is equation 3. So which is for position 2 and position 3. Position 2 and position 3 which are being present there. So this one is given as plus sign. So position 2 and position 3 are being given. So phi x overall, that is the flux linkage, is given as 1/3 of phi x1 plus phi x2 plus phi x3, which is being present there, which is phi x overall. So that's what you can generally understand from the given equation. So this is a simple substitution. All these things which are being given here are simple substitution. Let me just run through it quickly to see to it that if you understand by mathematical relations and grouping of terms and simple log formulae, logarithm formulae, you will be able to understand all these steps which are being given out here, and considering it to be a balanced 3-phase system. So whatever that we are doing here, we are not considering the effect of any fault or any other extra applications which are being there. So which has been applied to any 3-phase system, which has been connected to any such loading conditions or something like that. We are not going to analyze anything. We are just going to find out what is the inductance level that is being present here. So next one, what do I need to do? I need to analyze with respect to all these things which are being present here. Okay. So this one is the first equations what we have got. So after dividing it by 3. So as I regroup the terms, I'll be getting these terms which are being present there. So 3 times x being present. So 3ix into ln of 1 divided by r dash. So again ix is being grouped, iy is being grouped, and again next you have iz, and this one is given as iz there. Okay. So next what you can generally think of it is, so you will be having this term which is being present, and later for a balanced system ix equals minus iy minus iz, or I can generally write it as minus of iy plus iz there. Okay. So next moving on, you will be having the values which are being given there. So 3 times ix plus ix minus ix is being there as a common factor. I've taken the common factor as the point which is being present there, and iy plus iz is taken as a common factor, and minus ix is being given there. So next later on, I will be having these terms which are being got there. So let me group the terms carefully. So ix is taken as a common factor here. So if I want to group the terms now, so how do I group it? So, and again, if I want to take the inverse of it, so I'll be writing it as positive as 2d cube. So you can erase it here. I can write it as m squared h, that is inverse, and again write it as plus 1 here. Okay. So that's what you can generally come across in this equation. 2 into 10 power minus 7 into ix ln of these terms which are being present there. So 1/3 of the same thing. So ln a, okay, I can write it as ln cube root a. This is a simple formula which you can analyze. So after regrouping the terms, you'll be getting the final result as Lx, that is inductance, that is Lx equals 5x by Ix, 2 into 10 power minus 7, ln of 2/3, 2 times 2 power 1/3, d by r dash, m by n 2 to the power 2 by 3, Henry per meter there. So inductance of each phase, that is equal to half of inductance per conductor. So inductance of each phase, which is 2 into 10 power minus 7, ln of 2 times, that is 2 power raised to 1 by 6, d divided by r dash, 1 by 2, m divided by n, 1/3 Henry per meter. So you can write it in terms of Henry per kilometer also. The same term, ln, the same term is being replaced here. So this was the end of the derivation. In the next session, what we are going to analyze is with respect to the capacitance. Entirely, we are done with inductance now. We are going to deal with capacitance in the coming class. Okay, thank you.